Hi everybody and welcome to another JASP video tutorial. In this video I want to go ahead and take a look at the final t-test, which is paired sample t-test. You can find my other two t-test videos on this playlist and in info boxes here up in the right corner. I'll ping them a couple of times, one per video. So today, like I said, we're going to go through the final t-test example, t-test kind of test for frequentists, which is paired samples t-test. And as always, for this video tutorial series, I am using the current build version, the preview release JASP 0.10 to discuss what it is we are doing. So here is the welcome screen. We are going to go ahead and jump into the data. Okay, so after a quick cut, I have the data open. I have the mood and aggression sample data file where you can get it through the data library, and you go to categories t-test, and it is down here with the t-test in the t-test folder, mood and aggression, and it is the sample one included in the JASP program files as an example for paired sample t-test, and it's really simple. We have 15 observations for moon and other variables, and I'll go ahead and pull up the description. So this was from the Moore, McCabe, and Craig Introduction to the Practice Statistics 7th edition. So it's from their book, and Moore grabbed this particular set of data is part of a larger study by Nancy Edwards and Alan Beck measuring dementia patients. And so we have two variables, as I said. Moon is for the average number of disruptive behaviors among dementia patients during full moon days, and other is the average number of disruptive behaviors during other days for those same dementia patients, which is critical for paired samples t-test. You have two measurements from the same person. So if we go back to the data, the 1 through 15 here is 15 different people with two measurements. One for moon, so full moons, and one for the other days of the months. Okay, and so those are the average across several months. And the null hypothesis for this example is that there is no difference between the average number of disruptive behaviors among patients with dementia between full moon days and other days, that there's no difference. And so we'll go through how you do this in JASP in order to answer that question, in order to test that null hypothesis. So here we have the starting output for the paired samples t-test. Again, there are some, we'll say, defaults here that we can include, but again, we will go through each of these options except for the Vivok Selke maximum p ratio, as I mentioned in my independent samples t-test. We are not going to go over that in this, but we will discuss the other statistics. Okay, let's jump into the example here. So the first thing you need to do is you have your variables on the left, you need to add them as pairs to the right. So I'm going to go ahead and click on moon, and then click the arrow to the right. Now you can see that it puts in this gray box with two slots. And so if you're going to do multiple pairs, you can run multiple pair tests at any given time. They'll just start forming a vertical list here. And so you'll need to select the other one, and when you click the arrow to the right, it automatically throws it into the other box for the pair. You can see the slight blue highlighting here that makes it a pair. And over here in the results output, you can see that a very simple student's t-test of the moon average minus the other day's average yields a t with certain degrees of freedom and a p-value from from that t-value and those degrees of freedom. You can usually find t distributions in the back of most statistics textbooks. So we have a big t-value, small degrees of freedom, technically, but a very small p-value. It's less than the standard 0.001 marker. And so that is for the student t-test. So that's the basic output for that. But before I go into the Wilcoxon signed rank, as you may have seen in the independent samples t tutorial video, is I want to check my normality assumptions for both moon and other. So I'm going to go ahead and check that box and scroll down the results screen, and we're going to check the assumptions that I have a normal distribution for my difference score. As you can see, this is moon minus the other. So in a paired sample t-test, you essentially get the t-value from the difference between your two pairs of scores. So we'll call it capital D difference as opposed to Cohen's D, which is usually marked by a lowercase d. And so this is the difference score, moon minus other, and whether or not that distribution is normally distributed. And so we get a W from our Shapiro-Wilk test. Okay, that W value will let us know whether or not we are have a normal distribution, and whether or not that is a deviation from normality, and so we get a corresponding p-value. Now, there are different conventions for what the p-value is, what is considered a significant result for this p-value, what the alpha is that you're comparing this p-value to. It's not the same alpha as this p-value up in the paired sample t-test. Sometimes it could be, depending on how conservative or liberal you want your assumption check to be. But in any case, 0.05, 0.01, 0.001 alpha level, this p-value is clearly higher than that, and so we can make the assumption here that our distribution is normal, which means we don't have to do anything other than the student's t-test, which is the parametric, more powerful test at detecting an effect. But for the sake of fullness in this tutorial, imagine that this wasn't a normally distributed difference score. And so I have to then use the Wilcoxon signed rank test. So I click that box, and this gives me the non-parametric sort of ordinal response to moon minus other, for example. So moon is 1 and other is 2, and they're ranked somewhat, which is the ordinal interpretation of that if I don't have a normally distributed difference score. And so I end up with Wilcoxon test statistic that gives a value that also has a p-value associated with it. And you can see that there's essentially no difference for the two tests. They give you the same result. It's essentially how you have to interpret and then report these statistics that is important. Okay. Before I move on to alternate hypothesis or alternative hypothesis and what these selections mean, I'm going to jump over to additional statistics so I can just include these in my table over here. So we have the location parameter. This is the mean difference score, so it's the score of moon minus other in both cases, and there is a standard error associated with that location parameter. And And then I can get a confidence interval for that location parameter. So that's my upper and lower for 95% confidence interval. I can also get my Cohen's d effect size. Okay, Cohen's d effect size. This is the distance between the two means of my sample, and so we use the typical 0.3, 0.5, 0.8, 0.3 being a small effect, 0.5 being a medium effect, 0.8 being a large effect, and you can see here that this is a significantly large effect. I can also get the confidence interval for my effect size, which gives you the range for these particular effect sizes. The effect size for Wilcoxon is a match rank by serial correlation, rather than the distance between the two means. I can get my descriptive statistics table, which is always good. Gives me an n, my means, my standard deviations, and my standard errors of the means. I can also get a descriptive plot, which gives the confidence interval error bars. Well, they're not actually error bars. So confidence intervals, these are not standard errors of the mean. And so if you wanted to plot this line graph with the means but use standard error bars as opposed to confidence intervals, you would have to enter this into another graphical software, Excel, for example. I have a video about creating simple APA figures in Excel. You can spot that in the right-hand corner there. So those are the additional statistics that you can get with the paired samples t-test output. Missing values, we can exclude cases, analysis by analysis, if we had multiple variable pairs that had different missing values across. So if moon had a missing value, but then, I don't know, another pair didn't have that same missing value, you can exclude cases, analysis by analysis. So all the people that are valid in a particular pair will get run through the test, as opposed to list-wise exclusion, which if any person has a missing value, they will get excluded from all analyses. Okay, and so it depends on what analysis you're doing and whether or not you can interpret missing values appropriately from test to test. Okay, now the last part I wanted to show is the alternative hypothesis section. So we have 3, and it's a radio button, so we can only choose one at a time. For the first one, matches what this example suggests, which is that there's just no difference. And so the alternative hypothesis would be that there is a difference. But we're not putting a direction to that difference. We're not saying greater than or less than, as the other two would suggest. We're saying that moon average is different from other average, and that's it. Okay? This effectively cuts our alpha to the two sides of the t-distribution. Okay, so instead of 5%, we have 2.5% on the left and 2.5% on the right tail. Okay, now this just tells you that there is a difference between the two. And luckily, with the paired samples t-test, if you don't choose one of the directional hypotheses, and there is a difference, well, you can clearly tell that one is higher than the other, because you end up with either a positive or negative number. Positive being moon would be higher, and you end up with a positive test statistic. If other was bigger, if the average for other was bigger, then you'd end up with a negative test statistic here, and you can say, oh yeah, well, that one's bigger. Okay, because it all depends on the order. The numerator of the t-test has the sign for the minus, and so you don't always switch the order. It's the absolute value, of course, and you can always look at the means to see which one's bigger, and you can clearly see that the moon mean is quite a bit bigger than the other mean, 3.022 minus 0.589. So you can make that eyeball distinction. But just in case you had a directional hypothesis, you can, and instead of the null hypothesis being that there is no difference, the alternative hypothesis is that there is a difference and that moon aggressive behaviors are greater. So when there is a full moon, dementia patients exhibit more disruptive and aggressive behaviors, then you would likely choose this one. Okay? Now, nothing changes about the statistic. And that's because this test statistic, a t of 6.452, is significantly in the tails of the t-distribution. Okay? The interesting thing is that there is no upper limit for this effect, these confidence intervals, because we did a one-tailed test. So we've only looked at one side of the distribution. Okay. Now, if we suggested that, there's nothing to this moon myth, there's no such thing as a lunatic, even dementia patients, then we could say that, the average disruptive behaviors on other days are more common than moon days. Then we can say that moon is going to be less than other. Measure 1 is less than measure 2, and we can change that around. Again, the test statistic doesn't really change, except for the fact that if I have moon and other in this order, I end up with a p-value of 1. And that means that the directional hypothesis that I suggested for the alternative hypothesis that there's no difference, but in fact that moon will be smaller than other, is completely not true. It doesn't come out in this data, because the 6.542 is in the wrong tail for a critical value. Okay? And so we end up with the inability to detect a lower 95% confidence interval parameter, for both the effect size and the standard error difference. Now, the effect size doesn't change because that doesn't take into consideration the directional hypothesis, okay? And neither does the location parameter. And so you're like, but wait, there is no effect, but why is there an effect size? Well, that's because that doesn't take into consideration the p-value. P-value is not included in the effect size, which for some is better, okay? But here we can clearly see that, if we were making these alternative hypotheses a priori, and you definitely should, then we'd be wrong, because we would end up, as you can see, with the opposite pattern. So that thinking, when we choose one of these, is really important that we have a grounding in both the literature and what our descriptive statistics suggest, which is, either do measure 1 is not equal to measure 2, the non-directional two-tailed test, or the clear one-tailed test in what would be considered the appropriate direction, with the myths about lunatics and full moon fever, etc. And it would be ill-advised to choose this last one. But I included it, of course, to show you what would happen to the output if you had the wrong direction for the paired samples t-test. So that is how you run a paired samples t-test in JASP. Please leave your comments and feedback down below. that'll do it for this episode. Thanks so much for watching. Bye-bye.